Hello everyone, today we're going to look at lesson 3, gravitational potential energy. So far on these videos we've realized that energy is weird, nobody really understands it, but we can also keep track of all the numbers, and that's our job. Gravitational potential energy is no different. It's a very strange idea. It's really described in much more detail with Einstein's general relativity, and essentially the curving of space and time. And this image here really sort of helps us see that. You can see that, if this horizontal line here represents kind of the fabric of space-time, an object like the Earth, which has a large mass, bends that fabric of space-time, so there would be a big ripple, if you like, or a big indent in that space-time fabric. You can imagine if this was the fabric, putting a heavy mass in there, then the fabric would stretch down, leaving this curved fabric here. And then any other object that interacted with this space-time would essentially feel some sort of gravitational attraction. Now the moon also causes the space-time to bend, and you can see that there's this kind of ripple or this curving of the space and time here. But that's one way of thinking about it. The one that we're going to use is our straightforward gravitational potential energy equation, and you've probably seen this before. It means that the gravitational potential energy that an object experiences is proportional to its mass. So if there was an object, let's say there was an object here at position A, the mass of the object would affect how much gravitational potential energy it would have. It's also proportional to the gravitational field. That here is represented by the curving of the space-time from the Earth, and that's fixed on the surface of planet Earth. It doesn't change. Obviously, and hopefully you can see that as you move further away, that this gravitational value does change, it decreases, and we're going to learn more about that later on in this course. But for now, essentially, if you're on the surface of Earth, you can assume that it's just constantly the same as 9.81 meters per second. And then, of course, the other thing that it's proportional to is how far away you are from the surface of Earth, so mgh. And so here we are with our little equation. It's probably worth just switching our physics principles over to uniform fields compared to, on the previous image, we had sort of three-dimensional fields. So uniform field would essentially imply that the Earth is flat. I know that's not something you'd often hear in physics. Flat earthers tend to be derided, but in this case, if we zoom in enough, the surface of Earth essentially looks flat, and that means when we represent our gravitational fields, we can draw them all parallel to each other, and that means that wherever we are in the gravitational field, whether we're at position A or we're up here in position B, the gravitational field strength is going to be the same. In other words, it's a uniform field. It's a uniform gravitational field. Okay, now there's the equation that we just saw. Checking the units, of course we have kilograms for the mass, we have meters per second squared for the acceleration due to gravity, and then we have the height in meters. And if you put all that together, you're going to get kilogram meters squared over second squared, and that, my friends, is a joule, and that's good news. Okay, so the other big deal we've come across in energies is really defining the system, and that's where we get to in this case. We need to be able to define a system, and we can do that however we like. In this case, we're going to want to define a height reference point to be 0. And that means we have some sort of reference point with a known value. Once we've defined that, we're probably going to want to keep that to be the same unless the question or the scenario involves some sort of variation on that. But hopefully you'll see this played out in this particular example. So we have a 350 gram object that is a mass of 0.350 kilograms. Now, gravitational field, this is on the surface of Earth, so it's going to be 9.81 meters per second squared. And we have a height of 64 centimeters, so that is 0.64 meters. And then there's a change in the energy. There's a change in that gravitational potential energy, and that is 800 millijoules. So 800, now milli is 10 to the negative 3, so it's a small change. Okay, so those are our variables. We need to determine the final height. So let's go ahead and set up the scenario. I'm going to go ahead and say that this here is my 0 height. So my object is initially at a height, let's call this height 1. It's initially at this height. It's at 0.64 meters. Okay, there it is. It now gains some height 2, and this is going to be equivalent to a change in an energy, gravitational potential energy, of 800 times 10 to the 3 joules. Okay, so we need to determine the change in that height. We need to get h2, and then we can figure out the final height, and hopefully you can see the final height is going to be this whole height added together. So let's look at this height 2. We're saying that the change in this gravitational potential energy is 800 times 10 to the negative 3 joules, and that's going to be equal to the mass of the object times gravity times h2. All right. So that means that H2 is going to be 800 millijoules divided by the mass times gravity. And when we put those numbers in, we get 0.2329 ... meters. So when we add them together, the new height, the final position, that would be up here. The final position, so H is going to be h1 plus h2, and that means that the final height is 87 centimeters. Okay, so example number 2, we have classic little cart on a track scenario. We have position A and position B, and we're going to look at the total mechanical energy at those two positions. Now, what's interesting about this scenario is that we're told that to set the 0 height, so 0 height, well, actually I should write that height equals 0 at point A, so it has, as far as we're concerned, because we have determined the reference point, it has 0 gravitational potential energy at position A. It does have some kinetic energy. It's got EK, so it's got this kinetic energy associated with the speed, and that stays constant. Okay, so let's first of all convert that to meters per second and to meters, because that already makes me a bit nervous. Let's do our unit conversions. 11.2 kilometers over hours, and I'm going to get rid of the kilometers, so denominator, numerator. 1 kilometer is 1,000 meters, and I've got my hour there, the denominator, so numerator, denominator. 1 hour is 3,600 seconds. So actually in meters per second, the speed is 3.11 recurring meters per second. So that's the speed, and that does not change. The height, initial height, so height 1 is 0.8 meters. And of course the mass is 0.25 kilograms. Okay, so let's look at the energy, the total mechanical energy at position A. Total mechanical energy at A, well, there's no springs in this system, so we're dealing only with the kinetic energy and the gravitational potential energy at A. Okay, so do we know those numbers? Well, we know the height, we know the speed, and we know the mass. So yes, we do. We could work that out. At position B, so total mechanical energy at position B is going to be the kinetic energy at B plus the gravitational potential energy at B. Do we know those numbers? Yes, it's had a change in the height. So there's some potential energy there. There's the mass, and the speed is going to be the same. So we have all the numbers. Putting it all together, so you can see that the mechanical energy is kinetic energy B plus the potential gravitational energy at B, and those are all just known values. So here's the value for the kinetic energy. It's just simply 0.5, so half times the mass times that speed squared, easy peasy. That works out to be 1.209 dot 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 plus mgh. Well, m is 0.25, g is always 9.81 meters per second squared. Now, interesting, look, this is a negative, so this is important. We defined our reference point to be here, this 0 point, which is a little unusual, but totally fine to do. You can define your reference point to be anywhere you like, and that is set by the question or the scenario. And that means that the change in height is actually downwards. That's a negative displacement, so it's going to be a negative sign. And when you multiply those together, you get a negative energy. Now, that's not to say that energy is a vector in any way, but it's important that we keep track of the positives and negatives for the sake of bookkeeping, essentially keeping track of the values. And that means that overall, when you add them together, you end up with some energy being lost, negative 0.75. Now, let's just think about that qualitatively for a second. It does make sense. If your reference point is here, and you go lower and you drop down, then you are losing some energy. The gravitational potential energy was higher at this point and lower at this point. So because the velocity stayed the same, then the only thing that changed was your position in the gravitational field, and that is decreased. So you now have less gravitational potential energy and therefore less mechanical energy overall. This is going to be an important concept later on when we get into gravity in a future topic. This idea of decreasing energy as you get closer is a key concept, comes up in gravity, comes up big time in particle physics, etc., etc. Okay, that's it for now. We'll see you next time.